Poisson process expresses the probability of the given number of events occurring in a fixed interval of time. For example, it can express the probability of the number of visitors is 2 during 1 hour, or the probability of the number of visitors is 5 during 2 hours. And we should know that if these two time intervals are not overlapping, the probability of the number of visitors should be independent. And because the mean function is lambda t, so the longer the time interval is, the more visitors the hotel would have. And for the Poisson increment, it is defined in this form. And we can note that for the autocorrelation function, the value between the negative epsilon and positive epsilon is like a triangle. And it is very interesting that when epsilon goes to 0, the triangle becomes an impulse with area lambda. So the Poisson increment process is introduced to prepare us to define Poisson impulse process. And this triangle is with area lambda, which is independent of epsilon. And point impulse process defined like this function. The process d of t minus lambda have 0 mean and autocorrelation. That is for this autocorrelation function. And if the mean is 0, the d of t minus lambda is a white noise. In real world, there are some short noises as in the figure below. We may define it as the output of a linear time invariant system with the impulse response h of t and input as a Poisson impulse process. The underlying experiment is again the random selection of points with density lambda. That is the probability of getting k point in time interval 0 to t. And figure of x of t is like that. When t is 0, when the x of t is fixed 1, then we call it a semi-random telegraph. And if the value of x of when t is 0, if the value of x is a random variable taking 1 or -1, then we call it a random telegraph. For the random telegraph signal, the stochastic process is defined as follows. And when we try to guess the mean function, we can use some equation and we would get this result. The xt is defined based on Poisson point again. The number between t1 and t2 is a Poisson random variable with parameter lambda t. When t goes to infinity, which match our expectation, the probability should go to the half. And when the expectation is 0, when t is infinity, which means when in a very long time the expectation of the number of the event should be 0, because we can see that the value should be 1 and 0, and the probability of it get 1 or 0 is random, so it makes sense that the expectation value is 0. And for the random telegraph signal, it just have one difference between the semi-random telegraph signal when the t is 0, and it have the equal probability that that value is 1 or 0 or -1. So we can note that the expectation value should be 0, and the autocorrelation function is like that. For the random walk, it is very like when we toss a fire coin n times, and k is the value, is the number of heads in n toss, and when the coin is head, we have one step to one direction, and if the coin is not head, it's the tail, we should go back to one step to the reverse direction. So when n goes to infinity, we would have the normal distribution. The autocorrelation function contains a term, the mean value of t1 and t2, which come from the probability of independent increment. And we can make an example like for a drunk person, it can go to one direction for one step, and it can also take one step to in the reverse direction. And what is the relationship between what is the distance between the original point and the drunk person when the time goes to the infinity? And it should like the Wiener process. If the step is fixed, it should like the random walk. If the step is in the, if the step obey the, if the length of the step obey the normal distribution, it should be the Wiener process. So when we add switch limit to the random walk, we can get the random process.